Welcome, dear students. Today we will see the discussion on round robin scheduling algorithm. I believe that you might have gone through my sharing knowledge series on round robin and watched my previous video series lecture. So today we will see some numerical problem that is being covered from the perspective of the university exams. As the name indicates, the round robin is a preemptive process scheduling algorithm, and this type of algorithm is basically designed for the time sharing systems. So you will see that every process is being distributed based on the time sharing situations. And moreover, this particular scheduling algorithm is very close to FCFS scheduling algorithms, which you might have observed in my earlier video slides where I have discussed on the FCFS and its numerical problems. FCS basically stands for the first comes, first serve scheduling algorithms. Here we will discuss with respect to the one of the numerical problem which has been given in the table as PIDs. That is, a 4 process is being shown, arrival time is there, and its execution times, burst time is being given. And such type of a scheduling algorithm has one more important component is that normally along with the question paper they will give a time quantum. They will give a word like a time quantum, and here time quantum is mentioned as a 20 unit. Unit means whether it is a second, millisecond, microsecond, whatever it may be. So 20 unit we are giving. Now this is apart from this particular scheduling algorithm, you have to remember that this is a preemptive scheduling algorithms. And what is preemptive and non-preemptive scheduling algorithm I have discussed more in detail in the various class of discussions. In short, preemptive is that scheduling algorithms in which once the process starts running, you can stop the CPU in the middle and give the chance for the other process. And non-preemptive is that one in which once the process is running, you cannot interrupt the CPU, and the process after completing the task, then only it will release the CPU. That you have to understand. So this is a preemptive. So how to solve this process? Now in the Gantt chart we should start writing. Now you have to remember that this is almost all like a FCFS, but here we are not considering the priority, so I am deleting that particular column. So we will take the first process, say P1. When we take the first process P1, so arrival time is 0. So first process will take how much times? It will not process for the total 53. That means from here to first process is 53 unit times, and a second process is 17 unit times, third process is more than that, 68 unit times, and the fourth process is 24. So we cannot run the whole process for the one fixed time. Why? Because this is a preemptive. Preemptive means every CPU has to take care of the other process also. So what we will do is that in the first process 0, we will take a 20 unit time. So minus 20, 53 minus 20. 53 minus 20 is equal to 33, and we add 20 here. So 20 plus 0 is equal to 20 here. Now after P1, the next process is what? The next process is 17. The next process is P2. So that is P2 here. The burst time, you can see that burst time is very low, because in the case of a round robin, it is more or less similar to the nature of the FCS. So here the P2 will process 17, because 17 is less than 20, so the whole 17 we can take it, so it becomes 0. So we can add 17 to 20, so automatically it becomes 37. After P2, the next process is P3, because it's like a FCSM, it is like a round robin. So 1, 1, 1, like that it will keep on moving. So we go with the next process is nothing but P3. So when we put the P3, the next process will take how much? It will not be 68, it will take 20 units. So 68 minus 20 is nothing but 48, and we will add 20 to here, so it becomes 57. After P3, which is the next process, it is P4. So P4 will come, it is 24. So 24 minus 20, it is 4. So we will add 20 to here, so it becomes 77. Now after P4, which is the next process comes, you will see that here this process becomes 0. That means this process is over. Its task is over. The remaining 4 processes there. So after P4, the next process is P1. So we will write P1 here, and how much time it will execute? It will execute for 20. That means from 48 minus 33 minus 20 is nothing but it is 13, and we add 20 to here, it becomes 97. After P1, which process will comes? It will be P3, because P2 is over. So P3 will come. So in the P3, how much? It is 20. So it is 24 minus 20, it is 24, and here it is added 20, is nothing but 117. After P3 is what? P4 process. So we will write P4 process. P4 process is only 4, so minus 20 is almost all, it is 0. So we will add 4, because we cannot add 20, because its burst time is only 4. So plus 4, so it is 1 to 1. After P4, which is the next process, again it is P1. So P1 will execute for how much times? It will be execute for minus 20. That means in this particular case, it is almost all close to 0, and plus 13. So when you add it, it becomes 134. After P1, which is next process, that is your P3. But P3 will execute for how much times? 20 unit. You cannot add 24. Like in the earlier case, in the after the turnaround time is achieved, we are adding like a non-preemptive. So here 134 plus 20 is 154. Then again we have to add one more P3, where here it was 4. So here 134 plus 4 will come here. So that becomes 162. So then it becomes 0. So you have seen here is that each process has taken its execution time very as per the quantum time Qt. So based on the Qt, this particular process is being executed. Now what is next? Now we have to see the CT. But before going to CT, let us see one thing is that when the process starts, within the 20 quantum time, all the 4 processes has been arrived, because arrival time is 3, and within that 3 falls within this 0 to 20, where the process P1 falls. So our ready queue is between this 0 to 20, where the process P1 caused all the 4 processes to arrive in a queue. So all the 4 processes will be starting and will be lying in a queue in this particular order. Now we have to see the CT. We will see the CT from here, which process is at the last. So if you see that in this one, the P3 process, which is being mentioned on that particular scenario, it starts at the last point. So CT, if you try to see, you see this one is process P3 162, and then P3 we will ignore. Then P1 is how much? 134. Then P1 then comes 162 over 134 over. Then P4 completion time is how much? It is 121. And then we go further, and we see that P2 completion time is at 37. So this we have got. Now I am leaving this exercise for the students by watching my previous video series slides mentioned about the round doping. You see how the time of turnaround time and the waiting time is being calculated, and you calculate the average waiting times. I am giving a tips. Average turnaround time is nothing but total turnaround time divided by number of processes. So turnaround time means what? It is CT minus AT. So this minus this, you write, 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 then sum total. So let us take this is X, and here this sum total is Y. So this is nothing but X divided by number of processes 4. So you find the answer. Similarly, average waiting time. Waiting time is what? Total waiting time divided by number of processes. So just like here, how you calculate it. So you add the total Y and divide by number of processes. That is. And one more thing I would like you to calculate. You calculate throughput. Throughput is nothing but the number of processes divided by the last completion time. So how much is number of processes here? Number of processes is 4. What is the last completion time? It is 162. So that is the answer. So these 3 things you try to compute. Okay. So this is a exercise based on my previous series slides which I have been put for the students to learn. Thank you.